Hello all, we're going to look at some integration by parts. This technique is very popular when you're asked to integrate problems that have a product of algebraic and transcendental functions. And what I mean by that is maybe you have x squared times sine x or x squared times e to the x and you're asked to integrate that. I've put a checklist in here to help you itemize and label the u and dv parts. So let's start with the definition. If u and v are functions of x and have continuous derivatives, then the integral of u times dv is equal to u times v minus the integral of v du. Now, the way you pick a u and a dv, which will be the items from your original problem, is it's a good idea to, and I put this acronym, LIATE, logarithmic functions, inverse trigonometric, algebraic, trigonometric, and exponential. That's what this acronym stands for. The higher your function is on the list, that's the one that you would want to label with a u. The one that's lower on the list is what you'll assign to dv. For example, if we're asked to integrate x times e to the x dx, x is algebraic and it's multiplied times e to the x, which is exponential. Algebraic, exponential. Algebra ranks higher than exponential, so your algebra term, you let u be that one. The lower ranking one, dv. The original differential dx will go with whatever you assign to dv. Okay, so algebraic, that's our u. Exponential, ex dx is our dv. So that's what this ranking system is. If u is x, then du is dx. If dv is ex dx, then its antiderivative is e to the x. So you'll take the derivative of whatever you assign to u and the antiderivative of whatever you assign to dv. Once you know u and its derivative, dv and its antiderivative, you go back up here and you follow this expansion. U times v, that's x times e to the x, minus the integral of v du, e to the x dx. So this is our expansion, uv minus the integral of v du. The first half stays the same. The antiderivative of ex dx is e to the x plus our constant of integration. A follow-up example, we have the integral of x squared times natural log of x dx. Algebraic, logarithmic. Which one ranks higher in our list up here? Logarithmic. It ranks higher than algebraic. So u is going to be equal to our logarithmic part, natural log x, and dv will be the lower ranked one, x squared dx. The derivative of natural log x is 1 over x dx. The antiderivative of x squared dx is x cubed over 3. Now, following our expansion formula, u times v, that's x cubed over 3 times natural log of x, and remember with multiplication you can do it in any order, minus the integral of v du, that's x cubed over 3 times 1 over x dx. This 1/3 I'm going to pull out. X cubed over x is x squared. The first half you leave alone, minus 1/3 times the integral of x squared dx. This integral has an antiderivative of x cubed over 3 plus c. Don't forget this negative 1/3 because it'll be multiplied with it. Final answer, x cubed over 3 natural log of x minus 1/9 x cubed plus our constant of integration. Let's do a definite integral. We have the integral from 0 to 1 of arc sine x dx. Arc sine is a sine inverse. Dx is our differential. Now, we don't have the product of two types of functions, so what we'll do is we'll just pretend that this is arc sine of x times 1 dx. And what that'll do for us is, from the checklist, inverse trig ranks higher than algebraic because 1 can count as an algebraic term. So u is equal to arc sine of x, and it has a derivative of 1 over square root of 1 minus x squared dx. Don't forget in your Google Drive folder, you're more than welcome to have those readily available to look up these derivatives. If dv is equal to dx, which is an understood 1, then its antiderivative is just x. You follow the same formula. It's u times v, so that's x times arc sine x. With a definite integral, you evaluate the first half at your upper and lower limits minus the integral of v times du, v times du. Well, that x will just set up here in the numerator when you multiply. Notice the integral limits stay the same because we have remained in a variable x the whole time. Now, from our past assignments, we have learned to integrate using u substitution. Now, this is u sub, this is not integration by parts. This up here was integration by parts. To get this integral calculated, I'm going to let u be 1 minus x squared. The derivative will be negative 2x dx. Note that this problem has x dx. I'm going to divide both sides by negative 2, and x dx can be replaced with negative 1/2 du. If you use u substitution with a definite integral, then you've got to be careful to put your upper and lower limits through the substitution. Our top number 1 goes in for x, 1 minus 1 squared, that's 0. Our bottom number goes in for x, 1 minus 0 squared, that's 1. So our integral is going to have 0 on top and a 1 on bottom. That's why it looks silly here, is because I had to follow the order of translating the upper and lowers to new upper and lowers. All right, now notice this minus sign and that negative 1/2, that's going to make a positive 1/2 times the integral of 0 to 1. Well, let me rephrase that, 1 to 0, it's bottom to top. Meanwhile, up here, using fundamental theorem of calculus, we have the top number subbed in, that's 1 times arc sine of 1 minus 0 times arc sine of 0. Well, the angle that has a sine value of 1 is pi over 2. The angle that has a sine value of 0 is 0. So this first bracket, this part, simplifies to pi over 2. Now, let's go back to the integral part. The two negatives made a positive half, du. This was my substitute, so it's really 1 over the square root of u. 1 over u to the half, and then once it's moved up, it's u to the negative half. Add 1 to your power, that makes it positive half. Dividing by a half is the same as multiplying by 2. And if you also notice, I reversed the 0 and 1 here. You're allowed to do that if you negate the integral. So I put this note over here in green that you can reverse your upper and lower limits provided you put a negative in. So this positive will become negative again, half times 2, u to the half. Subbing in 1 and 0 for u, I get pi over 2 from the first half, these twos cancel, so that's minus 1 to the half, minus 0 to the half. Square root of 1 is 1, square root of 0 is 0, so this all becomes a 1. Pi over 2 minus 1, this is the exact value of the definite integral, and this is approximate to 3 decimal places. In the second example, and we're going to come and I'm going to show you how to do this one again later in the video, we have x squared times sine x dx, algebraic times trigonometric. Algebraic ranks higher than trigonometric. A is above t in Lie8 from the first slide. The derivative of u is 2x dx. The antiderivative of sine x dx is negative cosine x. Expanding, we have u times v, that's negative x squared cosine x, minus the integral of v du. So we have minus the integral of v du. These two negatives will make a positive, and I'm going to pull the 2 out. This integral is still algebraic times trigonometric. So algebraic ranks higher than trigonometric. The derivative of x is dx. The antiderivative of cosine x dx is sine x. Everything after this 2 is a second round of integration by parts. So I put a bracket, uv, that's x sine x, minus the integral of v du. So we have negative x squared cosine x. Distributing, that's plus 2x sine x, minus 2 cosine x, because that's the antiderivative for sine x, plus c. Let's look at the integral of secant cubed. Now this is a weird case of where sometimes you have to rely on trig identities to break this up. Secant cubed x means that there's 3 secant x's multiplied together. I'm going to go ahead and split this into 1 and 2. So this is actually secant x times secant squared x dx. Now, sometimes you just have to rely on luck. Put something down. I just randomly chose u equal to secant x. And it just takes time and experience to get used to these. Believe me, I still have to erase and try again on quite a few of them. The derivative of secant x is secant x tangent x dx. Don't forget you can look these in your Google Drive folder and under the formulas folder. dv is the other 2 secant squared x dx. The reason I left 2 of them over here is the antiderivative of secant squared x is just straight up tangent x. U times v, that's secant x tangent x, minus the integral of v du, which is tangent times secant tangent dx. Stack them all in there. Those 2 tangent x's can be written once with a square. That's totally appropriate. Now we're down to secant x tangent x minus the integral of secant x. Remember from your Pythagorean identities in trig, tangent squared theta is equal to secant squared theta minus 1. So that tangent squared x can be rewritten as secant squared x minus 1. Why did I do that? Because I knew eventually that I would have to try to get both of these integrals done. So we have secant x tangent x out front, distributing that secant cubed x. It feels like you're spinning your wheels because that's the original problem. This is one of the tricks in Cal 2 that you'll have to run into now and then. Distributing here, negative secant times negative 1 is positive. So basically what I did was I distributed a secant x, and I made sure that negative sign was accounted for on each distribution. Since this negative integral in the middle is identical to the original problem, I'm going to write the integral of secant cubed x dx, which is our original problem, is equal to secant x tangent x minus, basically I just wrote the original problem with the expansion here. I lightly underlined these two integrals because if I take this one and move it over, it becomes positive. It's just like solving an equation. You're solving it for the integral of secant cubed x dx. Now once I move this one over, I've got two of them. And that's equal to secant x tan x plus, we've looked at this integral before, and if you need to use your formula sheet, that's totally fine. The antiderivative of secant x is natural log absolute value of secant x plus tangent x, plus our constant of integration. By moving this integral over, since it was the same as the original problem, I've got two of them. But notice on this side of the equation, I don't have any integrals anymore. It's all expanded. Divide all the way through by 2, and lo and behold, our original problem is equal to half of secant x tangent x plus half of natural log secant x plus tangent x. Half of a constant of integration is still a constant of integration. And so that's a trick where sometimes while you're doing integration by parts, you run into the original problem in the middle of your expansion. Now that integral that we did earlier, that was the integral of x squared sine x, algebraic ranked higher than trig, so we let u be x squared and we let dv be sine x dx. We had to go through the integration by parts twice, and sometimes that just happens. So what we do with that problem is we can look at a tabular method for problems that involve repeated integration by parts. We picked x squared to be u, so what I'm going to do is, the way this works is you set up alternating signs, positive, negative, positive, negative. Whatever you pick for u, write that down. Take its derivative over and over until you hit 0. Take dv, which in this case would have been sine x dx, and keep taking antiderivatives as many times as it takes till you hit 0. From your alternating signs column to your u column, you go straight across. So positive x squared. On your dv column, you slant down to the one below. Don't go straight across. So positive x squared times negative cosine x, that's negative x squared cosine x, minus 2x times negative sine x, which is a positive 2x sine x, plus 2 times cosine x. Luckily, we didn't have to worry about any signs on that third. And then when you get to 0, you don't have to do anything because 0 times whatever is still going to be 0. Don't forget your constant of integration. This one takes a little bit to get adjusted to. It does work. I hope this video has helped out. If it gives you any trouble, integration by parts, reach out by phone or email, ask problems in class, stop by the office, and I'll do my best to help you out.